Okay, so good evening, everyone. Let me just turn on the camera. Yeah, so good evening, everyone. Welcome to this session on doubt clearing, basically, live session on problem solving of the course network analysis EE54, the course code. So, today we will be looking at assignment 2. And previously in assignment 1, I hope the whatever problems we solved, those were understandable, and I hope you were able to understand how I had explained, how I had solved. And still again, if you have any doubts, I please do comment on the YouTube channel. I will try to address the doubts. And today we will be looking at assignment 2, and today we will be actually solving the problem. So like unlike previous week, where I had already solved the problem, and I was explaining you step by step. So today, this week, we will be actually solving it step by step and looking at every details. And then obviously, if you have any doubts, you can stop me and I will help clarify the doubts. And then obviously, you will be, getting the material. So you'll be getting this recorded video as well as the material that I'll be, using for teaching. And then you can use that to understand the problems. Again, if you have any doubt, you do please comment on the channel, on the video, and I will try to address the problems. So without further delay, let's start. So I'll just share my screen. Okay. I hope my screen is visible. So, so here is the problems for assignment 2, and we will be solving it step by step for every problem. And of course, I will be turning my camera off. So I will be allowing the mic to each of the people who are entering. And just if you have any doubt or anything, just stop. I mean, just raise your hand. There is a raise hand option. So just stop me and please ask your doubt and please get it clarified. Okay. So, Prakash, just if you could let me know whether you are able to see my screen, just if you could just raise your hand or unmute and speak. Either of the two will work. Can you see my screen? Okay. Fine, anyways. I hope the screen is visible. So let's start. So we will be solving, we'll be looking at each of the problems step by step, and I'll be solving this. So we'll go in order. So let us look at the first problem now. So the this is basically a graph where the current IA, that is obviously amperes, current in amperes, it is shown. I mean, the variation of current is plotted against time, and the time is in seconds, and the current is in ampere, the unit. So they are asking that the current is given above, so this figure. Calculate the voltage across the capacitor at t equals to 1 second. So basically to solve this we need to know how my capacitor voltage is related to current, right? And then only we would be able to proceed further. And obviously this statement is very important, that the current when initially uncharged capacitor is given above. So initially uncharged, right? So my basically if I write here, so my q0, right, q0 is 0, right? So it basically represents that my this capacitor was uncharged, right? And this 0, this basically means that at t equals to 0, so at time at equals to 0, so at time t equals to 0 the capacitor is having a charge of 0, uh, you know, coulomb, 0 coulomb. So we know how the voltage, capacitance, and charge of a capacitor are related. So it is nothing but Q equals to V into C, right? So V is the voltage across the capacitor, C is the capacitance of the capacitor, and Q is the charge developed by the capacitor. Now we need to write an expression for the current. So this current is I equals to, as we know that it is dq dt, right? So it is the rate of change of charge with time, right? So uh, this therefore, I mean, if we substitute this here, so basically this would be what, d dt of vc, right? So therefore, I mean, if in this problem my the capacitor is initially uncharged, it is told, and the, you know, the capacitance is constant, so it would come out of this d dt thing, and my resultant voltage expression would look something like this: d dv dt. Okay. Therefore, if we try to find out the what is the voltage, so it would be something like this, right? I dt. And if we try to find out the voltage, we need to perform an integration of I over the entire time period. So if I just use another color, so this is my voltage to current expression for a capacitor. Okay, so this is very important. You need to arrive at this expression for solving the problem, and it is very straightforward because it is plus two level questions. You have already, you know, learned this in class 11 or 12, right? Probably class 12. Okay. So in this question, they have asked us to find out what is the voltage across the capacitor at t equals to 1 second. So basically, from basically for over this entire period of time, we need to find out this. So if you look at this expression, right, v equals to 1 by c integration of I dt. So this is nothing but the area over the curve, right? So if you consider a curve like this, where I is varying over time, so it is nothing but voltage would be nothing but the area under the curve, provided I mean, yeah, it's pretty simple. So it is area under the curve. So this would be what, so if I try to calculate the voltage, so we need to consider specific time intervals. Okay. So basically now I will be just substituting the value of the capacitance. So 1 by 50 millifarad, right? So 1 by 50 into 10 to the power minus 3, right? And now these are the integrations, and I will be taking each time period. Okay. So this from, let's say, let's take from 0 to 0.2 second, and let's integrate over that. So what is the value of current from 0 to 0.2 second? It's nothing but 5 amperes, right? So in place of I we need to write 5, and dt will be dt, it won't change. Similarly, from 0.2 to 0.4 second, what is my current? It is nothing but my 10 amperes, right? So it would be 10 dt. Now again, from 0.4 to 0.6, what is my current? It is nothing but 5 dt. Again, in this way, I mean, it would be what next would be 0.6 to 0.8. So again, this is increasing to 10, right? So this would be 10 dt. And finally, from 1 to 0.8 to 1, it would be nothing but here my current is 0, right? Because it has decreased. You can clearly see that this is 0. So this would be 0 dt. And in this way, so we have been told to find out at t equals to 1. So basically at t equals to 1 means you need to use this formula and find out the what is the voltage developed across the capacitor over this period of time, right? So this would be what my 10 to the power 3 would go up, and this is my 50, right? And then I just need to integrate it now. So this is very simple integration. So t, this would be over a limit of 0 to 0.2. Then this would again be over a limit of 0.2 to 0.4. Then this would be over a limit of 0.4 to 0.6. Then this would be over a limit of 0.6 to 0.8, and finally obviously this would be 0, so I am not writing because this is the current is already 0 here. So therefore my what would be my voltage? So this would be 20, right? 10 to the power 3 means 1000 divided by 50. This would be 20, and the current would be what? It would be 0.2 minus 0, so it would be 0.2. I am directly writing it. So this would be what? 10 into 0.4 minus 0.2, right? So again 0.2. Then it would be what? 5 into 0.6 minus 0.4. So this will be 5 into 0.2. And same here also, 10 into 0.8 minus 0.6, 0.2. This is 0. So very simple. We need to just now. So this would be what? 1. 5 into zero point 0.2, then 10 into zero point 0.2 would be 2. Then again 1, then again 2, right? And this is 0 obviously, and this is volts total. So in this way, the voltage that we will be getting. So this would be what? 20 into 6, right? So my voltage would be, my resultant voltage would be 120 volt, and this is at 1 second. So this is the voltage that is developed across the capacitor at t equals to 1 second. So this is the entire process for the question, and let me just use a different thing to highlight that. Yeah, this is the answer. So my this is my answer. So this is the voltage at t equals to 1 second. So this is my answer. So this was how you will be solving. So I hope this is clear. So basically here you need to find out, you need to know how my charge, voltage, capacitance are related, and then you need to obviously substitute the expression that current changes with I mean it is dq dt. Obviously rate of change of current is charge is current, and then you need to substitute and you need to arrive at this expression, right? So which is nothing but area under the curve. And I mean, a substitute of this would be to directly, I mean, instead of integrating over each time period, now from 0 to 0 0.2, 0 0.2 to 0 0.4, 0 0.4 to 0 0.6, you can directly find out the area under this curve, right? So basically, you would be breaking this into a rectangle, right? So this would be what my this would be 5 into 0 0.8, right? And this would be what? This would be 10 minus 5 into 0.2, right? 0.4 minus 0.2. Similarly, here also 10 minus 5 into 0.2. So this would be what, 1. This would also be 1, and this would be 4, right? So, and this is already 0 because this current is already 0. So we need to find till 1 second. So this would be what, 4 plus 1 plus 1. So this is 6. So this is the current IDT. Basically, IDT is nothing but this, and you need to multiply this. So 6 into 1 by C, right? So 1 by C is nothing but 50. So this comes out to be 120 volts. So this way you also can solve the problem. This is another alternative way, but I here I showed you the conventional way of actually finding it out. So it's up to you how you actually solve the problem. So I'll just erase all of this. So I hope this was clear. Just let me erase all of this. Give me some time. So those who have joined late, please try to join on time if you are willing to join this live session. And I mean this. So if you haven't understood this problem, don't worry. I'll be uploading this video. You try to watch the video, and if you don't understand, comment on the YouTube channel regarding the which question you didn't understand, and I will try to solve this. Address the your doubt. Okay, and so if anyone has any doubt, I mean those who saw the question, so if anyone has any doubt, please, there is a raise hand option. Obviously, you can use that and just let me know whether you are able to, what is your doubt. So I'll just let you speak. Right now, going on. Okay, so now let us go to the next question. So here, so this is a common data question for question 2 and 3. Now here they have told that there is a 200 millifarad capacitor is connected to a voltage source such that the capacitor voltage varies using this formula. So it is nothing but an exponentially decreasing. So it is decreasing exponentially, right? So 5 into e to the power minus t. So it would be something like this. So initial value would be 5, and it would be decreasing something like this, right? So this would be your voltage, and this would be your time. And the initial voltage is 5 volts. So VC at t equals to 0, right, is 5 volts. So this is pretty straightforward. Now they have asked us to find out what is the energy in millijoules stored in the capacitor at t equals to 1 second, right? Um, so um, for solving this, we need to find out. Yeah, okay. So we have been told to what is the energy in joules, right? We need to find out that. So my energy in joules, what is the formula? So it is nothing but half CV square, right? As we know, for capacitor it is half CV square, right? Yeah, so it is half CV square, and we have been told to find out what is the energy stored in joule or millijoule, whatever, at t equals to 1 second. So uh, now it is this problem is very simple. So we know that the expression of the voltage when t equals to greater than 0, right? So when Vc at t greater than equals to 0, so what is the expression? It is nothing but 5 into e to the power minus t, right? And so what would be the voltage at t equals to 1 second? So it would be nothing but, so Vc at t equals to 1 second would be nothing but 5 into e to the power minus 1 volt, right? And therefore using this expression, so energy at t equals to 1 second would be nothing but your half c into Vc at t equals to 1 second, so iska square, right? So this would be nothing but, so what is c? C is 200 millifarad, so 200 divided by 1000 into 5e raised to minus 1 whole square, right? And this whole in joule. So I have already solved this. Now, if you try to solve this, you would be getting something around 0.3383 joules. So we have been told to find the answer in millijoule, right? Just be careful of this because this is a numerical answer type question. So if you by mistake, if you put this number, your answer will be wrong, because for this kind of questions they do provide a range. For example, so the correct answer would be 338.3 millijoule, right? So they would be setting a range of maybe 335 to 340. This is the range for the answer. But if you put this value, then the range, it would be out of range, right? And hence your total answer would be wrong, but you actually did solve it correctly, right? So just be careful of this, in what unit are they asking, so put the answer according to that. Okay. So as a result, okay, so this is my final voltage, final energy in millijoule, and this is what the capacitor has stored in t equals to 1 second. So let me just use a different color. This is the final answer. I just again explain the problem once. So a 200 farad capacitor is connected to a voltage source such that the capacitor voltage varies as this. So right. So at t less than equals to 0, it is 5 volt, and at t greater than equals to 0, it is 5 into e to the power minus t. Therefore, this voltage versus time relation would be something like this, right? And my capacitor, so it would be kind of exponentially decreasing, and my capacitor, the energy stored in the capacitor is half cv square. Now at t equals to 1, what is the voltage of the capacitor? It is 5, just you need to replace t by 1 second. So it is 5 into to the power minus 1 volt. And then what is the energy at t equals to 1 second, right? So it is half c Vc at t equals to 1, right? So this, just you need to replace this value over here, and you'll be getting 338.3 millijoule. So this is how you would solve question number 2. I hope this is clear. If you have any doubt, just raise your hand. I will try to solve. I will try to clarify this. If you have any doubt to this question, just raise your hand. You have a raise hand option. Please raise your hand. So these materials would be provided, and in the last week, as you saw, I had already solved the problems and then uploaded the answers. I mean, solving. I was explaining the each and every problem to you by explaining each and every steps. Here today, what I am doing, I am trying to solve it in front of you so that you are able to understand each and every step. Okay. And if you have any doubt, you do comment on the YouTube channel after I upload this video, and you will also be getting this material. Okay, so now let us go. If you don't have any doubt, let us go to question number 3. So now here they are asking what is the amount of energy, right? So this is connected to question number 2 only. Okay, so as you can see, common data for question 2 and 3. So they are asking what is the amount of energy in millijoule lost by the capacitor between t equals to 0 and t equals to 1 second. Okay. Now for this, how shall we approach the problem? So we will be calculating what is the energy stored at t equals to 0 second, and we obviously did calculate what is the energy stored at t equals to 1 second, which was nothing but 333.3 millijoule. Basically, after that we would be finding out the difference between these two energies at t equals to 1 and at t equals to 0. And I mean, since this is exponentially decreasing, right? So obviously at t equals to 0, my the energy stored in the capacitor would be greater. So uh, I mean, at t equals to 1, it would be obviously less. So that is it. So the just the difference between these two would give me a number. Okay. Therefore, the energy at t equals to 0 second would be what? So first of all, what is my voltage at t equals to 0 second? So Vc at t equals to 0 is nothing but e to the power minus. So what was the expression? 5 e to the power minus t, right? Okay. So shift it here. Yeah. So it is nothing but e to the power minus t. So here we will be placing 0, right? So this would be nothing but 5 volt, because this is time t equals to 0, and therefore the energy would be nothing but half into Cv square. My C is 200 millijoule. Uh, uh, sorry, millifarad. I'm really sorry. This is 5 square, and this is joule. So this would be coming out as, so you can easily calculate this, right? So at 5,000, this would be 25, and this would be what? This would go. This would go. Uh, okay. Hmm. V square. Uh, okay. So should be what, 200,000. Okay, yeah, I did a mistake. So this two will cancel. Then this would be what, 5, right? And this 5 will get cancelled. So this would be, I'm really sorry for the delay. So this would be 5 by 2 joule or 2.5 joule, right? And what was the energy that was calculated at t equals to 1 second? So it was around 338.3 millijoule, right? So therefore, what is the energy lost in the process? So energy lost equals to energy at t equals to 0 second minus energy at t equals to 1 second, right? So this is nothing but 5 by 2 minus 0.3383 joule, right? This would be what, 2.5 minus 0.3383 joule, and this would be what, your 2 point. Okay, yeah, this would be something around 2.3 here. Yeah, 1618, I think, joule, something like that. Okay, yeah. So this is the basically the amount of energy loss. So this is the energy lost by the capacitor between E at t equals to 0 and at E at t equals to minus 1. Okay. So this is the answer, final answer for this question. And this was a very simple problem, provided you understood the first problem where we were told to find out the what is the energy stored at capacitor at t equals to 1 second. And here also we need to find out what is the energy stored by the capacitor at t equals to 0 second. And then we know what is the energy stored at t equals to 1 second. We just need to find out the difference between the two, and we will arrive at this number. So this is very pretty simple problem. Okay, you would be easily able to solve this. So I hope this is clear. And if you have any doubt, I think you can speak out, Prakash. So if you have any doubt, I'll just wait for 1 minute. If you have any doubt, you can speak up. Otherwise, we'll proceed to the next problem.
Doubt, sir.
Okay. So okay. So next problem is something like this. So here, so again, this is a common data question for question number 4 and 5. At steady state. Okay, so steady state, I mean, what do you mean by steady state? So see, in this kind of problems now, in this transient, so this is basically transient analysis, right? This is nothing but your transient analysis in circuit theory, and it is very important, one of the important chapters of this subject. This is transient analysis, where you would be finding, switches opening and closing. They would be telling you, okay, find the switches getting closed at t equals to 0, or maybe some time, after some time. So, and the circuit would comprise of capacitor. Your circuit would comprise of capacitor, or maybe inductor L, along with resistor. So either this or this, or this or this would be there, or combination of each of these would be there. Okay, these type of components you would expect in this transient analysis. So means you would be understanding that t is equals to infinity. So a long time has passed since you had first applied the voltage. So a long time has passed. Infinite means a very large number which we can't count, right? It could be anything. It could be 10 to the power 9, 12, anything, right? Second, any unit. So basically a long time has passed. So that is what we mean by steady state. And there is another problem, that at time equals to 0, I mean, another part of this problem, we will be coming to this kind of problems later. So another problem would be that at initially, so at the initial state, which basically means at time t tending to 0 or t equals to 0. So at t equals to 0, the switch is closed. So then what would be the behavior of the inductor? What would be the initial voltage to the circuit? This kind of problem. So here, for example, what is the voltage at steady state, right? So these kind of problems you will expect. Okay. Now this initial state and steady state, how the capacitance and inductance acts, that you need to know. Okay, probably you would have seen the videos, seen the lectures, and probably you know how the inductor or capacitor works in the steady state or at time equals to zero. So I'll just make a table for you, maybe here using current. So let's say this is my time. Okay, this is my C, this is my L, and I create a table here. So this is time t tending to zero. So see, understand this. So basically, at time t equals to zero, my capacitance, you know, it will be initially uncharged, right? So I mean, if the capacitance don't have any voltage, right? uh, I mean, it is not charged initially. Let's say the capacitor is not charged initially. So my initial assumptions would be something like this. Okay, so initial assumptions of both C and L would be something like this, that my C and L and C both are uncharged, right? So this is very important. So both L and C are initially uncharged. Now, since this is uncharged and we are applying some voltage to charge the inductor or either the capacitor, so how would their how would they perform over time, right? So at t equals to 0, the capacitor, now since it would be developing some voltage across it, right? So initially you won't expect, so as soon as you apply the voltage, you won't expect any charge build up instantaneously at t equals to 0. Therefore my capacitor, writing it like this, SC means short circuit, and my inductor would be nothing but just the opposite. So it would be nothing like but an open circuit, because inductor, what it does, it allows current to pass through it, right? Because the energy given by the inductor is nothing but half Li square, and the energy given by the capacitor is half CV square. So since at t equals to 0, um, I mean, as soon as uh, turn on the circuit, you won't expect any charge build up randomly, instantaneously through the capacitor or through the inductor. So my capacitor would be acting like a short circuit, and my inductor would be acting like an open circuit. Now at time t equals to infinity, it would just be the opposite. It would become an open circuit, and this would become as a closed circuit. This is why this also has a reason. So at t equals to infinity, my capacitor, there would be a complete voltage build up across the capacitor, and hence it would get charged up. So as soon as the capacitor gets charged up, it it tends to act like a voltage source, and I mean, in some cases, it acts like an open circuit. So yeah, so that is why, you know it would be something like this. So it would be an open circuit, and for the inductor, this would be acting like a short circuit or a current source. So we'll be coming to that, but for the time being, you understand this, so you need to remember this table. So at time t equals to 0, my capacitor acts like a short circuit and my inductor acts like an open circuit, and vice versa at time t equals to infinity. Okay, so keeping this in mind, we can solve the problem. So this problem is very easy. Now at steady state, they have told us. So at steady state, and since this is a capacitor, so at steady state, that is at t equals to infinity. What is this? This is nothing but an open circuit, right? So my resultant circuit would be what? I'll be just drawing it. It is a very simple problem, provided you understand this. So this would be nothing but, this is 40, this is 10, right? And this is open source, right? Because this is open circuit, and open circuit means this is open, right? And we need to find out what is the voltage across this open circuit terminal. So and this is basically 10, this is 40, and this is 2 volt. So this, what is the voltage across this open circuit terminal? So now if you just remember the analysis, the nodal analysis that we had performed in the last week. So this open circuit voltage is nothing but the voltage across this terminal, sorry, and the voltage across my this terminal and this terminal. Basically, if I represent it like 0, node 0, and this is my node 1. So why I am telling this, because in this circuit also you will see that the capacitor, so if this is connected across node 1 and node 0, so my capacitor is connected across between these two nodes, right, between these two resistors. So VC, this plus VC is nothing but the voltage across 10 ohm resistor, right? It is very simple. So we just need to find out what is the voltage developed across this 10 ohm resistor. So, what is the current flowing through this? It is very simple. It would be nothing but, so this, since this is open circuit, I mean this part won't be taken. So my 40 and 10 ohm are connected in series. Therefore, this would be what, 40 plus 10 ampere. So this is nothing but 50. 2 by 50. I'm doing nothing, right? Okay. So I won't simplify this. Now, what is my VC? It is nothing but the voltage across the 10 ohm resistor, and my 10 ohm resistor is this. Okay, so voltage is this. So this is 2 by 5 volts, right? So this is 0.4 volt. So this is my answer. This is pretty simple. Okay, very simple. So this is at steady state. Voltage at steady state. This is because at steady state we saw that the capacitor acts like an open circuit, right? Because if the capacitor has developed this much charge, this much voltage, basically it has developed 0.4 volts at time t equals to infinity at steady state, and hence it acts like an open circuit. So this is how we solve the problem, and this is your answer to question number 4. Okay, so now let us just move to the next problem. We'll move a bit faster. Now they have told what is the power being dissipated through the 40 ohm resistor. Now this is very simple, right? So what is the current flowing through 40 ohm? It is nothing but I. So therefore, power dissipated through 40 ohm resistor would be nothing but I square into 40, right? I square R comes from I square R, Joule's law of heating. Right? I would just remove. So this is nothing but Joule's law of heating. Right. So this is I square R, and again my I was what, 2 by 50. Right. So 2 by 50 into 2 by 50, and then this is 40. Right. So this would be what, this 5 would get cancelled, and obviously this 2 would also get cancelled. So this would be nothing but 125 watt, 8 by 125 watt. And they have told us to find out the power in milliwatts. Please always note this fact. I have told you the importance, because this is not MCQ question. You have to type the answer here. So in order to convert this into milliwatts, what we need to do, we need to multiply it by 1000. Pretty simple, right? So this would be what, this would be 25 to 100, and this would be 548. Yeah. So this would be 8, right? So this would be 64 million. This is the answer to the question. Pretty simple. Okay, pretty simple. You just need to know what is the how my capacitor, how a capacitor works in steady state or at time t equals to 0 when the switch is being closed. So that's it. Once you do that, the answer is straightforward, right? So now I hope this was clear. If you have any doubt, you can just speak up. Otherwise, I will just proceed the next question because we have a lot of questions today, around 15 questions. Okay, so now let us look at question. So this is again a common data question for question 6, 7, 8, and this is an inductor question. So the current waveform through so the current through this 100 millihenry inductor is given above. So this is the waveform of IT versus time. Now they are telling us what is the inductor voltage Vt at t equals to 0, right? Now here you need to understand. So in the capacitor, so here in the first question we saw how the voltage across the capacitor changes with time, right? Sorry, how it is related to the current flowing through it, right? So it was V equals to 1 by C integration I dt. Similarly, for an inductor also we need to know that, and it is pretty straightforward. You have surely read in your plus 2 level. So it is, so inductor across voltage across inductor is nothing but minus L di dt, right? So this is the expression here, right? So now basically see, it is pretty straightforward, right? So they have told us to find out what is the uh, my Vt at t equals to minus 500 millisecond. Okay, so minus 500 millisecond would be what? It would be something here, something like this, because it would be minus 500 means what? It is minus 5 second, right? Divided by 1000. So here it would be something like minus zero point 0.5 second, right? So here this would be minus zero point 0.5 second, and if you see between minus 1 to 0 second, from this period to this period, my current is increasing linearly, right? So this is a straight line equation. Clearly you can see there is no doubt in this, and my minus zero point 0.5 second somewhere lies in this. So it is a linear equation, and I mean, the current would be, I mean, you can easily find this, right? So you can find out the slope of this. So di dt would be nothing but the slope of this line, and the slope at let's say at minus 0.7 second would be same as minus 0.1 second, because this is a linear line, and in a linear line, increasing or decreasing it may be, we expect that the slope remains constant. So this is the basic funda. So mm, didt would be what? My final current. What is my final current? It is nothing but 2 amperes here. So 2 amperes minus what is my initial current? It is 0 minus dt, right? Dt is nothing but final minus initial. What is my final current? This is 0. Sorry, time, and this is my initial time. So minus of minus 1. So therefore this would be 2. So didt would be 2. So 2 ampere per second, basically the unit. And so VL would be what? Um, so VL would be um, this minus L, right? Minus L is what? My L is what? 100 millihenry, so 100 by 1000, and this is 2, and this would be volts, right? And this would be 0.2 volts. So here you don't need to, uh, take the magnitude, I mean, take the sign into consideration. You can just take the unit only, the magnitude only. So probably the final answer would be VL. And if I just consider the magnitude, it would be 0.2 volts. Okay. So this would be the answer. Right. So this is the answer. So again, I mean, just to explain the problem again quickly. So you need to know how the inductor voltage across the inductor is related to the current flowing through it. So it is VL equals to minus L di dt, and di dt. Since we have been told to find out what is the inductor voltage at t equals to minus 500 milliseconds. So in this period, we need to find out what is the slope, right? So di dt is nothing but the slope of this line, right? And since it is an increasing line, so the slope would be positive. And I mean the slope again, the slope at minus zero point 0.5 second would be the same as at this point, at this point, at any point on this line, right? So because it is a linear line, the slope is expected to be constant. It is very simple. Now once you do that, you get 2 ampere per second as the slope, and now you just replace this in this formula. You know what is the value of L, you get it to be 0.2 volts. So this is pretty simple, and this is the answer to the question. Okay. So if you have any doubt, just raise your hand. Okay, yeah, yeah, Prakash, go ahead.
Can you tell me one more time, sir? I can't understand. That they
Which
ask
part?
0 0.2, but there is no use of 0.5 second in your slide, sir. If you
Yeah,
can find
okay.
uh, where you used the 0.5 seconds, sir.
See, this is the fundana I told you, na. See, from my, just let me use another color. See, from t equals to minus 1 second to t equals to 0 second, what is my current? So it is increasing linearly. You don't have any doubt in that, right?
No, sir. There is no
Yeah,
doubts.
the current is linear increasing
Yes, sir. Linear, sir.
linearly, right? Now, see, now as I told you, you need to know this voltage expression, right? So it is VL equals to L di dt. So what do you mean by di dt? It is the
Sir,
slope
I
of
have
this
one more
line.
doubt, sir. Sir, I have one more doubt, sir.
Yeah,
And
okay, tell it.
voltage formula VL equal to, I studied in my book L into DIBDT. Uh, where it's come from minus, sir.
So
I
see,
never.
this is based on EMF's law, right? So I mean, this is not EMF's law. This is, I mean, the voltage that it develops, na, the across the inductor, it tends to, repel the current that is, I mean, it tends to oppose the current. So it tends to oppose the cause which is developing it. So this is the basic law. So for this problem, if you have the doubt, since you have been told to calculate the magnitude of the voltage, you can easily ignore this sign. Okay. But there is a negative sign because the voltage that is developed across the inductor. So inductor is nothing but a coil, right? As you can see. So it is a coil that is wired around something, some a wooden piece maybe. And if you if you allow a current to flow through it, a voltage will be developed across it, which will oppose the flow of current, right? So since this opposed word is coming, that is why this minus sign is being used. So there is a law. This is well proved. You can easily find it out on the net. So that is
And
why this minus
I
sign
think
is
you
coming.
said the lens law, sir. I studied in
Yes,
lessons.
yes,
It's
Lenz
opposed.
law. Exactly,
Something it's opposed.
exactly. So that is why this minus sign is coming, right? Due to
Okay, so
Lenz law. You understood now, right? This part why this minus sign is coming.
yes, sir. No,
Prakash, your voice is
understood, sir.
breaking. Your voice is
I
breaking.
think I'm in low tower areas.
Okay, okay, okay. So,
You
okay.
hear me, sir?
Okay, so you understood this, right? Just tell me yes or no. Why this minus sign is coming?
Yes, sir. I understood, sir. I
Okay,
understood, sir.
okay, okay, okay. Now coming to this part, why this? Why aren't? Why? Why am I not taking minus 0.5 seconds since it is explicitly mentioned?
Uh,
Now, see, from -1 to 0 second, the current is increasing linearly, and in between this part, minus 0.5 is also there, right? 500 minus 500 millisecond is also there, right? So
yes, sir.
this is part of this line. Now, if I am to calculate the slope, right, di dt, so the slope at this point, right, at this minus 0.5 second would be the same as this here, would be the same as this here, and would be the same here, would be same here also, would be same here also, right? All over the line between minus 1 second to 0 second, right? So it doesn't matter whether they give you minus 500 millisecond or let's say minus 0.3 millisecond second, right? So minus 300 millisecond or minus 100 millisecond, it doesn't matter, because on this straight line, whatever the slope you may calculate at any particular interval at any time, it is constant. It is minus 2 2 ampere per second. Okay, so this is the funda, and that is why we are calculating the slope, right? And this is constant all over the line from minus 1 second to 0 second. And we use that to find out the value of the voltage at 0.5 seconds. So this voltage would be the same across at any point between 1 second to 0 second, minus 1 second to 0 second. So at maybe minus 100 millisecond also the voltage would be same. It has to be the same unless and until your inductor value changes, because didt is same since it is a straight line, in linearly increasing line.
Okay, sir. Clear, sir. Thank you, sir.
Did it get cleared, or you still have some doubt?
Okay, sir. Currently, I'm clearing, sir.
Okay, fine. See, if you still have doubt, you can ask me. You can comment on the YouTube channel. I'll try to explain it in a better way. Okay.
Question, sir.
Just remember that this is a straight line. This is a linear line, and didt over any point on this line would be constant. So it is. It really doesn't matter whether they tell you to find out 500 milliseconds. So 500 millisecond is important in that sense that you need to find out where this 500 millisecond lies, right? So see, if this was instead of minus 500 millisecond, if they told you plus 500 millisecond, so then it would be something around here, right? It would be something here, and this is a not a linear line, this is just a straight line, and at this point didt will be 0 because my current is not changing with respect to time, right? Here it was increasing with respect to time. From 0 it increased to 2 over time between 0 to minus 1 to 0 second, but here it is rather constant. So that is why here didt would be 0, and therefore the voltage across the inductor would be 0. So you need to calculate this didt. You need to understand what is the physical interpretation of didt. It's nothing but the change of current with time. How with time the current is flowing across the inductor. Is it increasing linearly? Is it constant? It is decreasing, or is it 0? You need to understand that.
Yes, sir. I'm understanding, sir.
Okay. Okay, so now here they have told us what is the voltage Vt at t equals to 1 second. So again, see, as I told you, what is the voltage at t equals to 1 second? So what is my current at t equals to 1 second? It is 2, right? It is constant from, see, from 0 to 2 second. If I write here, from 0 second to 2 second, my current is constant, right? The I flowing through inductor is constant. It is not changing with time, right? It is equals to what? It is equals to 2 amperes. It is constant. Here it was increasing with the time. Here it is decreasing with time. Here again it is constant. So therefore, I mean, if we, what should I say? If we find out the derivation of a constant, it is nothing but 0, right? So basically my di dt here would be what? So it would be d dt of 2 amperes. So since it is constant, so this would be 0, right? Therefore vl would be what? It is, if I take the minus into consideration, I mean, don't take it, so it would be what? L into 0. So this would be 0. This is my answer. So why 0? Because the rate of change of current with time is 0. This is clearly visible from this graph. It is not changing with time. It is 0, right? So that is why the current is, the rate of change of current is 0. The current is not 0, mind you. Please do understand that the current is not 0, but the rate at which it is changing with time. At 1 second is, it is also 2 ampere. At 2 second it is also 2 ampere. At 0 second also it is 2 ampere. Therefore, the rate is not. I mean, the rate is 0, but the current is not 0. Therefore, didt would be 0, and hence the voltage developed across the inductor would be 0. So this is question number what, 7. If you don't understand, please try to understand the concept of, I mean, I guess you need to go back and understand the concept of how voltage develops across the inductor using this LDI What is the physical interpretation of DI It's not just a mathematical equation. It's how the current is changing with time, that you need to understand. That is very important here. So yeah, now the next question is, so this is the final question of this 6 to 8. So next question is, what is the inductor voltage Vt at t equals to 2.5 seconds? So 2.5 seconds would be what? It would be something around here, right? It would be something around here between 2 to 3, and in between 2 to 3 you can clearly see that my current is decreasing, that the current is decreasing with time. Therefore here again the voltage would be what? It would be VL, if I ignore the minus, didt. Now what is didt? My initial current is what? Initial current means current at 2 seconds, right? Because here from 2 to 3 the current is changing, right? So what is my current at 2 second? It is 2 ampere. And what is the current at 3 second? It is 1 ampere. So my if I write a final current, sorry, 1 ampere. So this is 1 minus 2. And what is the time? It is between 2 to 3, right? So basically final minus initial, 3 to 2. So this is 1. And if I substitute this, what would be VL? This would be minus 1 into 200 by 1000 volts. This would be minus zero point 0.2 volt. Right, so this would be the answer. So here also you see that I don't take 2.5 second into consideration. This is mainly because it really doesn't matter. I mean, if the 2.5 second is the time period, they provide any time period, and if it falls between this time interval, now between 2 to 3, at any point, if they tell you to find out what is the voltage developed across the inductor at 2.7 second, it would be the same, because here the current is decreasing linearly, and the slope at 2.5 would be the same at 2.7, would be the same as 2.4. So therefore didt would be the same here, right? So didt would be nothing but minus 1 second. So therefore it would be minus 2 volts, zero point 0.2 volts. So this is it. So if you have any doubt related to this, raise your hand. I mean, I'll still try to clarify the doubt if you have any. Otherwise, we'll proceed.
No doubt, sir.
Okay. You don't worry. You read the book. I mean, this how this thing is happening. Why are we calculating the slope? You will understand. It is a very simple thing.
Okay, sir.
Okay. So similarly now coming to the steady state of inductor, right? So see, inductor may, we saw this table, right? If we go back to this table, right, at t equals to infinity. So if we look at this problem at a steady state, right? At steady state means t equals to infinity, very long time. We don't know what time it is, but it is a very long time. So that represents steady state. So at t equals to infinity, what is my inductor? It is short circuit, right? So we have to take this. We just need to remember this, and you need to solve this. Okay. So if I redraw the circuit, it would be something like this. So this is of course at steady state. Okay. And this would be something like a short circuit. Okay. So, could you tell me what is the resistance of a short circuit line? It's a very basic thing. If you could tell me what is the resistance of a short circuit. Hello?
Sir,
Yeah, please tell what is this resistance. So, this is 4 kilo ohm, right? This is 4K. This is 2K, and this is 24 volt. What would be the resistance across this point?
zero,
What
sir.
would, yes, this would be 0. So, therefore, I mean, if I calculate this thing, right, the equivalent resistance of 4K and 0, so R equals to 0. So if you do this parallel thing, you will see that this will get cancelled out, right? Because R1 into R2 divided by R1 plus R2, right? So R1 is already 0. So therefore your numerator would be 0, and then it is pretty simple. So therefore your 24 volt, right, this would be a circuit, and finally this is my circuit, right? So they have told what is the current flowing through steady state. So this is nothing but the current flowing through the resistance, I mean the inductance, right? Not the resistance, the inductance IL. And since this is shorted, this would be nullified, this 4K is nullified, and therefore the current that is flowing through the whole circuit is nothing but IL. Pretty simple. So this would be 2K, this would be 24 volt. Therefore IL would be what? IL would be um, so of course IL at, so just let me rest this. So IL at infinity would be nothing but 24 by 2K, right? 2K ampere. So I'll just not use this. So I'll use 2 milliampere. So this would be what? 12 milliampere. So this is the answer to this question. So pretty simple. I hope, provided you know this. So how an inductor works in the steady state. It is a short circuit, and you need to calculate the equivalent resistance of these two paths. You clearly see that this get nullified, and this is the current flowing through the inductance. So therefore, the total current flowing through the circuit is nothing but IL, and therefore IL is the current flowing through this resistor, and obviously the inductor here which is shorted. So therefore your answer is 12 milliampere. So I hope this is clear, pretty simple. And next is, what is the voltage at steady state, right? So yeah, this is very simple. So voltage at steady state means what? This voltage across this inductor. So this is nothing but this node voltage only. If I consider this to be node 0, and if I consider to be node 1. So if this thing gets shorted, na, if this thing gets shorted, right, as you saw, if this thing gets shorted, so what would be the voltage? Since resistance is 0, right? So V would be what? I into R. So my R is already 0, right? So therefore V would be 0. Pretty simple. So therefore my VL at steady state, so VL at infinity would be 0. This is very simple, because it is a short circuit condition, and short circuit, as you know, it causes fire, right? There are fires in the building due to short circuit. It is due to infinite, I mean not infinite, but a very large current flowing through it. So as a result, the voltage, the resistance of the line decreases, and the voltage also decreases, right? So in ideal case, so this is an ideal case, so the voltage would be 0, because my resistance is 0 and the current is tending to infinity. I mean, not infinity, but a very high current. Basically, here 12 amperes. So, since this is shorted, my R is 0. Therefore, the voltage drop across this path would be 0, and hence the voltage across the inductor would be 0. So, this is regarding question number 10. So, I hope this is clear. These two questions, question 9 and 10. Hello, Prakash. Do you want to say something?
Clear. It's very easy.
I am not able to hear you, Prakash. Your voice is breaking slightly.
Yes, I understood. It's very easy.
Yeah, so what you do now, you try to post your questions in the comment section. I'll try to address there, okay? That would be better.
Not thing there.
Or you do one thing now. See, there is a chat section here, right? As you can see on the screen, there is a chat
But
section here. You can write the doubt here. Okay, so type a new message. You must be getting something like this. Please write here. I'll try to address that.
sir, I'm using in smartphone, sir. Chat disabled, sir.
Okay, okay. Okay, fine. Then the only option is commenting on the YouTube video. So you do
Any
that.
doubt? No problem, sir.
Okay. Okay. Yeah. Okay. So let us now go to the next question. So this, which is question number 11 and 12. Now don't get confused when by looking at such a large circuit. This is a very simple problem, provided you know the how the analysis is being done. So what are they telling? Calculate the voltage Vx, assuming that the circuit is running for a very long time. So t tending to infinity, right? Steady state thing. So at steady state, what we saw, my L is what? The L is short circuit and the C is open circuit, right? OC. Therefore, you need to modify the circuit accordingly. And of course, this is an open circuit, right? So you just don't need to take into consider, because in the question only these two terminals are open. So you can consider this to be an open circuit. No worries. So if I redraw the circuit, what would be this? So this is my plus 5 volt source. This is the inductor at steady state. So as I told you, this would be shorted. right? So I have sorted it, and this is the resistance, and of course this is open, so I won't be drawing it. Just let us keep this open for the time being, okay? And now there is an inductor, right, and the capacitor connected in parallel. So basically this would be something like this, shorted, sorry, this would be open, really sorry, this would be open, and this would be shorted because this is an inductor. Yeah, the units are wrong here, in the question. So this would be 2 farad and this would be 20 Henry. The printing mistake probably. Okay. And this current source would be there. It won't get affected. Right. And now in this path, what is happening? This is a short circuit since this is a inductor, and this would be an open circuit. This would be an open circuit, right? And this is obviously the resistance, and this is another resistance, right? So this is 15 ohm, 15 ohm, this is 5 ampere, this is 20 ohm, right? And this is 5 volt. So we need to find out what is the voltage across this, right? So therefore, if I redraw the circuit, equivalent circuit, it is very simple. See, I am sorry. So this is turned on the other side. This is tilted. So really very sorry for my drawing, but I hope you are able to understand the main essence. Try to draw properly. So this is the volt. So I am just redrawing the circuit here. So this is 20 ohm. These all of these terminals are open, right? So this is open and this is shorted, right? So this would be something like this, right? Then this is 5 ampere. This is 15 ohm, right? I am not summing it up. This is basically this would be 30 ohm, but I'm just not summing it up right now, right? And this is 20 volts, okay? And this is 20 ohm, and this is 5 volt. This is 5 ampere. So this is my final circuit after shorting the inductance and open circuiting the capacitance in at steady state, right? So now we need to find out what is the, so just let me use a different, right? So we now need to know what is the voltage across this resistance, right? And I mean, let us try to solve this using nodal analysis, okay? This would be pretty simple using the concepts of last week. So this, let us consider this to be node 0 and this is node 1, okay? And as we saw in nodal analysis, we need to take one node as a reference node, right? So let us take this node 0 as a reference node and let us ground it, okay? So I would be doing what, I would be just shifting this to the other side. I'll be grounding it. I'll be applying a ground, okay? This is the basic concept of nodal analysis, provided I mean you would be knowing provided you watch the video of last week. So this would be what, so at node 1, let's say my voltage is V1, so the current flowing through this path would be what, 5, the voltage difference between 5 volt and at voltage at node 1, so this is V1, right, divided by the resistance of the path. This would be equal to what? So nodal analysis basically means incoming current equals to outgoing current, right? So 5 volt current, I mean the current flowing through this part would be dividing into this path and this part, right? So I have two outgoing current. So one is this 5 ampere source, this current, and the other is the current flowing through this path, right? So my voltage at node V1 minus the voltage at node 0. Now node 0, as we saw, so this is equals to 0 volt, right? My reference node, so this is 0 and this is 30. So using this equation, we need to find out what is the voltage V1, okay? So let me just simplify that. This would be V1 by 30. Okay. So, I mean, if you just now we need to just simplify this. So basically, okay, let us just solve this directly. So just taking the LCM of this would be what, 5 into 30, so 150 plus V1 divided by 30, and we don't have space, working space. So this 0 0 will get cancelled. So we will have 3 into 5 V1 equals to 2 into 150 plus V1. Okay. So this would be what, 15 minus 3 V1 equals to 300 plus 2 V1. So let us just take V1 to the other side. So this would be 5 V1, 3 plus 2 V1, and this would be what, minus 300 minus 15, whole of minus 15, right? So 5 V1 would be uh, minus 285, right? So V1 would be what, minus 285 by 5 would be what, 57 volts. Okay. So let me just take this to the other side so I have space for this. So the V1, the voltage at node 1 is nothing but this V1 minus 57 volts. So what is the current flowing this 30 ohm resistor? So each of, I mean, since this is connected in series, right, 15 and 15, the equivalent resistance is 30. So what is the current flowing through this path? So let us say that this is I2. Okay. So just let us say, okay, so I'll just use a different here for the sake of your understanding. So let us say that the current flowing through this path is I2, right? So I2 would be what? I2 would be what? I2 would be V1 minus 0 divided by this 30, right? As we solved it here. So V1 is minus 57 by 30 amperes. Now what would be Vx? Vx would be nothing but the voltage drop across 15 ohm resistor. So it would be 15 into 57 by 30. Okay. So this would be half, and this would be minus 28.5 volts. So this is my answer. This is a pretty simple problem, but the steps are a bit lengthy. I mean, you just need to simplify this circuit, okay? Provided you know that at short circuit my inductor works as a short circuit and the capacitor, I mean at steady state inductor works as a short circuit and the capacitor works as an open circuit. So according to that the circuit will get modified and you can use nodal analysis or mesh analysis to get what is the voltage at Vx. So this is pretty simple. Uh, so I hope this was clear, right? Okay.
Yes, sir, it's very clear, sir.
Okay, fine. Thank you. Okay, so see, now the next part is what is the open circuit voltage between X and Y, that is Vxy. Vxy basically means this point, right? So, I mean, if I draw it here in this circuit, so Vxy would be what? This voltage. So basically, there is a resistance connected. It won't matter because this is already an open circuit. So Vxy would be what? This voltage, right? And if I draw it here also, right? Here also it would be something like this, right? This would be xy. Now if we closely look at this, right? So this node, isn't it same as node 1? It is the same as node 1, right? And since this is ground, this y would be equals to 0, right? So I mean, if just let me redraw the circuit. uh, then there is a 15 ohm and 15 ohm connected from 5 ampere, 10 ampere, 10 ohm, and this is xy, and this we assume is node 1 and node 0. So this point and this point, they are same. So I'm just writing like this, and this point and this point are same. Therefore, Vxy is nothing but V1 minus V0. So basically, minus V1 was minus 57, and obviously V0 is 0. Therefore, Vxy is minus 57 volt. If you closely analyze, this is x is node 1 and y is node 2. Okay, so x is equivalent to node 1 and y is equivalent to node 0. Therefore, Vxy would be V10, that is V1 minus V0. So this is how we solve the problem, and this is the answer. Okay. So I hope this is clear. Okay, so this is problem number 13. So now only some few problems are left. So 3 problems are there more. After that, we'll end the session. Now this is a capacitor, and it is told that the capacitor was initially charged to 10 volts, right? So Vc0 is 10 volt. It is very important to note that Vc0 minus is 10 volt. Now I'll explain you why are they writing this minus sign here. So this minus sign, just use a different color. Okay, this minus sign is basically this minus sign represents the time before switch was closed. I mean, this minus only represents that. So V0 minus basically means at t equals to 0 just before the switch was closed. And if I write if I write Vc0 plus, so it represents the time just after the switch is closed. So basically here this plus would represent time just after switch is closed. Okay, so so these are the basic representations. So just let me, because we need some working space to solve the problem. Okay. So this is it. So they have told us that what is the uh, calculate the time required for the capacitor to discharge to 1 volt. Okay, now this involves time constant, right? Where we have working space. So this involves time constant because this is an RC circuit. So as you know, RC, RL, RLC circuit, these do involve time constant, and time constant of an RC circuit is given by R into C. So this is R is what 10 kilo ohm, means 10 into 10 to the power 3, sorry, and into C. C is what 10 millifarad, right? 10 into 10 to the power minus 3. So this minus 3 10 to the power 3 gets cancelled, and this is obviously the unit is in second. So since this is time, so this is 100 seconds. The time constant is 100 seconds, right? So the initial capacitance, the voltage across the capacitor, or Vc0 plus or minus, whatever you may write it, it is 10 volt. Okay. Now they are telling that the switch was closed, and what is the time required for the capacitor to discharge to 1 second, right? So for this we need to write what is the voltage expression across the capacitor. So see, this is very simple. Now, I mean, as you know that the capacitor, it keeps on decreasing exponentially, right? So since this the capacitance, I mean RC circuit has a time constant. So this tau is the time constant tau, and it decreases exponentially, right? So at t equals to infinity, what would be the voltage across the capacitor? So Vc, obviously at t equals to infinity, it would be zero, right? Because the capacitor is draining its voltage, and at some point of time, I mean, since a resistance is connected in series with it. So as soon as you connect a resistance to a capacitance which is charged initially, it will start to draw some current right out of it. And if you measure the voltage across it, you will get some voltage, right? So this is the basic funda. So the resistance will keep on drawing the current until and unless the voltage across the capacitor is zero, and that will happen at t equals to infinity. I mean, at a very long time. That is why we write t equals to infinity. So using this, so as you can see that it would exponentially, the voltage across the capacitor would exponentially decrease with the time constant of tau. Therefore, using this we can write the expression of this vct, right? So the initial voltage is 10 volt, right? And as we saw, it is decreasing exponentially as minus. So minus t represents exponential decrease, minus t by tau. Okay, because this tau is a time constant, so this would be nothing but t by 100 volts. So this is the expression of for the capacitance. So it is very easy, I mean, provided you know the concept. So this is the expression. Now they have told us what is the time required for the capacitor to discharge to 1 volt. Okay, so what is the time required? So let's say, I mean, we need to find out what is this time t at the Vc equals to 1 volt, right? So my voltage is 1 volt, and this is 10 into to the power t by 100, right? Okay, so um, now what we can do, so this is very simple. I mean, you just need to apply a logarithmic thing. So this would be what, e to the power 100 equals to 1 by 10. Now you apply ln, logarithm on both sides, right? So this would be nothing but ln of e to the power minus t by 100 equals to ln of 0.1. Now if you find out the ln of 0.1, okay, so this would be what? I'm just writing, simplifying the expressions for you. So this e to the power minus t by 100, this minus t by 100 would come to this side. So it would be nothing but ln of e into this thing. And this would be ln of 0.1. So these are basic logarithmic properties, you will know. So ln of e is 1, as we know. So this would be minus t by 100, and this would be minus, so ln of 0.1 is probably minus 2.3026. So this minus minus gets cancelled, and at the end you will have something like this, 230.26 seconds. So this is the answer. So they have told that what is the time required for the capacitor to discharge to 1 volt, right? So you need to find out the expression of the capacitance voltage, and you need to find out, I mean, once you find out that, you need to substitute what is the voltage here. So it is 1 volt, and by doing a mathematical operation you will easily get that time. But the most important thing is that you need to find out what is the voltage, the expression of the voltage through this capacitor and resistor connected in series. So I hope this was clear. If you have any doubt, you can ask.
No doubt.
Okay, don't have any doubt. We will proceed to the next question, and this we'll try to complete it. Okay. So this is another inductor based problem, and okay, so here we need to solve what is the, you know, expression for current through the inductor. And so we will go through it. So now at you need to consider two cases, right? So here they have told that the switch is getting close at t equals to 0. Before that there was no current flowing through the inductor, so therefore the initial current is 0, right? And hence if the initial current is 0, what would the inductor act like? It would be simple, it would be open circuit, very simple. And so at okay, so IL basically, so this IL equals to IT only. So IT equals to IL of t. Let me write this. So IT at IL of t at t equals to 0 would be what? 0, right? And and this IL at t equals to infinity would be what? At infinite I mean at time t equals to infinity, as we saw, this would be short circuit. So this would be short circuit, right? So it would be infinite, the current flowing through it. It would be really very high. Who is this guy trying to? Yeah. So now we need to redraw the circuit at two time instances. So one we have this at t equals to 0, and at another at t equals to infinity. So if we draw the circuit at t equals to 0, what it would be like? So at t equals to 0, as we saw that my inductor is open circuit, right? So if the inductor is open circuit, there is a resistance connected parallel across this current source, and the inductor is open circuit, right? So this would be something like this, and this would be 2, this would be 1, right? So this IL would be what? This would be simple, this IL would be 0, right? At t equals to 0, and at t equals to infinity it would be what? It is very simple. So this 2 ampere again, this is 2 ohm, and this IL is shorted, right? Because at time t equals to infinity, the my IL is shorted because infinite current is flowing through it. Therefore the resistance across this path is 0, we already saw that. And the equivalent resistance would be what? It would be, so R into 0 into 2 divided by 2 plus 0. So therefore this thing would get cancelled here, and therefore this would be something like, this thing 1 ampere, and this would be my IL. So IL would be what? IL at t equals to, hello, are you telling something, Prakash?
No, sir, no, sir.
Okay. So IL at t equals to infinity would be what? It would be 2 ampere, right? Now we need to frame the equation of IT over time, right? So this is just if I shift it a bit on the other side. So I'm just rewriting this. So this would be at t equals to 0, right? IL of t equals to 0 is this thing, 0. So the IT, right? What would be IT? So here IT or VT, in such cases these do have a formula. So please try to remember this formula. So it is given by I of infinity. So I of infinity basically represents IL of at t equals to infinity. So this is the formula. So I of infinity minus bracket of I of infinity minus I of 0 into e to the power t by tau. Okay, so tau is nothing but here L by R, right? So what is the L? L is 1 and it is 2, so this would be half, right? So this is the formula, and just you know, circle it because this is very important. It will help you to solve these transient analysis problems, right? So here you just need to substitute the all the parameters. So I of infinity was what, 2 ampere, right? Because I of infinity is time, and I of 0 means I L at t equals to 0. 0 means at time t equals to 0, right? So this is 0 again, t by 1 by 2, so 2t basically. So tau is 1 by 2, so 2 comes up, so therefore minus 2t. Therefore your it is what, 2 1 minus, so if I take t common, so this becomes 2t. Okay, so 2 into 1 minus e to the power minus 2t. So this is the my current expression. Okay, now they have told us how much time does it require for the current to drop to 0.8 ampere. So this is, once you derive this current equation, it is very simple. So how much time is required for the current to drop to 0.2 second, uh, 0.8 ampere, I'm sorry. So okay, so this I have done something wrong here. So this would be 1, huh? Only 2, sorry, because the current source is 1. I by mistake I wrote this 2 resistance here, 2 ohm resistance here, because the current source is 1 ampere, right? So therefore I L of t equals to infinity is 1 ampere, and therefore this thing will also be 1. I'm really sorry. This thing would also be 1, and therefore there is no need of bracket and all. I will rewrite this. So this would be nothing but e to the power minus 2. Okay. So we need to find out what is the current time required for the current to drop to 0.8 ampere. So we need to just substitute it, 0.8 minus 2t. So this is again very simple. E to the power minus 2t equals to 0.2 second, right? So again take ln on both side. If you take ln, this minus 2t will come outside. So sorry, this is e, and this would be ln of 0.2. Okay, so once you do that, the t that you would be getting would be close to 0.806 seconds. Okay, so this would be your final answer. So this would be your final answer. I mean, see, the basic concept here is that you need to, I mean, remember this equation, and this is valid for current as well as voltage. So, for example, you are given a capacitor, right, where the capacitor is initially uncharged and it is getting charged. So you need to find out what is the voltage across the capacitor with respect to time. So you need to know this formula. So here then it would be something like Vt equals to V of infinity, means V at time t equals to infinity minus V at time t equals to infinity minus V at time t equals to 0. That is initial state. This is steady state at t equals to infinity, steady state into e to the power minus t by tau. Okay, once you get this, you need to substitute, and before that you need to find out what is the voltage or current at t equals to 0 or at t equals to infinity. That you need to find out. Once you do that, you just need to substitute here and you will get an equation, and after that it is pretty simple. Okay, so I hope that this was clear, and so with this we'll be proceeding to the next problem. So I hope this was clear. The final problem now left. So okay, so what is the how much is the total energy in joule delivered or supplied by the current source after the switch is closed? Okay, so total energy in joule, right? So for that, let us calculate what is the power Okay, what is the power delivered by the current source? So they have told us what is the energy delivered or supplied. So let us first calculate what is the power delivered by the current source. So power delivered would be nothing but 1 ampere, because this is the current, into voltage across the 1 ampere source, right? Now what is the voltage across 1 ampere source? If we look it again. So let us just take that the switch is closed. Okay, I'm just redrawing this. So this is L, this is R, and this is 1 ampere. So this is the node here, right? This is a node, this is a node, and this node is common, right? So let us take this as 1 and 0, and this node is also same as this node, right? Because there is no other element attached to the right side of L, right? So therefore, the voltage across 1 ampere source would be what? 1A into V1 minus V0. So let us take V0 to be 0 volts, right? It is a reference node. So therefore 1 ampere into V1, right? So what is V1? V1 is nothing but the resistance, the potential difference across this inductor, right? So V1 would be what? Nothing but L di dt. This is the expression only, right? This is the potential difference across the inductor, right? So L di dt. So what is L? L is 1 Henry, and what is di dt? As we saw, this is e to the power minus 2t, right? So if we uh, make the derivation of it, this would be something like, so this would become 0, and here this minus 2 would come outside, and this minus minus would make plus. This would be e to the power minus 2t volts. So therefore the power delivered would be 1 ampere into 2 e to the power minus 2t volt, right? So this would be 2 e to the power minus 2t watt. So this is the power delivered. Right now, what is the energy? Because they have told us to find out what is the total energy. So total energy would be what? Total energy would be my power integrated over time, because it is basically the multiplication of power with time. So that is what gives us the energy in joule. And see, it is telling that what is the total energy supplied, right? So here we will be taking, so there would be obviously a limit to this integral. So this would be starting from 0, and this would go towards infinity, and I'll tell you why we chose this limit. Okay, so this would be joule and dt, obviously. Okay, so why this 0 and infinity? See, this 0, so let me use a different here. This 0 here, it corresponds to initial state of the circuit when t equals to 0, when the switch wasn't closed or was just about to be closed, and this is at steady state at t equals to infinity. So over the entire stretch of time, we need to calculate what is the energy being delivered by the circuit. So that is why we chose these two limits. Okay, and so this, if I do this, the integration to e to the power minus 2t dt, so this minus 2 would be coming outside, so this minus 2 into e to the power minus 2t, and this would be something like this. And as you know, e to the power minus 2t at t equals to infinity is nothing but 0, so this would be nothing but 0, and this would be 1. So this is 1 joule. So this is the answer. to the question. You need to be careful about the limits here. Okay, you need to choose over the entire stretch of period, because they are telling what is the total energy. Total energy means from starting to end. This is what we get. So this is the answer. So that is it for today's session. I hope at least some of the problems you were able to understand. If not, please do comment on the YouTube channel when after I post this video. I will try to address the questions, address your doubts. Okay, you have. And again, next week, same time, we will again be meeting, and we will look at assignment 3, and we will try to solve each of these problems slowly, step by step, as we did today, right? So I'll be uploading it maybe these all these materials by tomorrow. Okay. So yeah, if you have any doubt, please raise your hand, or I mean, I'll try to address your doubt if you have any.
There is no.
Yeah, Prakash, I can't hear you. Can you speak loudly?
Okay, sir. But the today's session was very, very helpful to me, sir.
What this material?
No, sir. The today's session was very useful to me,
Okay,
sir.
okay, 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 okay. Yeah, yeah, yeah. See, that is the purpose
I
of this
understand.
kind of live session.
I have a lot of doubts, sir, before this session, but now I was very clear, sir. Once again, I thank you, sir.
Okay, okay, no problem. Yeah, so this is the purpose of this session only. So that is why I tell everyone that please try to join every live session, so that each of these problems get clarified. And network analysis is a very basic course, and you would
Yes, sir.
be
I'm able to attend the class, sir. But today I have attended the class, sir. I was very sad last time why I am not attending the class, sir.
okay. Okay, yeah, yeah, no problem, no problem. Anyways, if you
Okay, sir.
can't attend, you will get
Meet
this
on
recorded
Monday, sir.
session.
Okay, sir. Bye, sir. See you on Monday, sir.
Yeah, yeah. Okay, okay. Thank you. Bye.
Ah, okay, sir. Bye, sir.
Bye.